Now let's move on to algorithms. So these are algorithms to compute eigenvalues. If we have a characteristic polynomial, finding its roots, polynomial equal to 0 and the roots of that equation is a very hard problem. So if we have a 100 by 100 matrix, no human being will be able to do it by hand, and computers will take a horribly long time to do this. One idea that I shared with you is a Sylvester's law of inertia. What you will do is to use the fact that the number of positive pivots is the number of positive eigenvalues. Easy to compute the pivots, Gaussian elimination, and that will give you the number of positive eigenvalues. Shift the matrix by alpha, eigenvalues will get shifted by alpha, and determine the number of eigenvalues above and below any alpha by shifting it here and there. Really encourage you to go and write this in Sage Math or in pure Python, because it's an interesting exercise. It's not a very good algorithm, I'm going to tell you right now, because you don't know how much to shift alpha by and when you can stop. All those things are not obvious, so it's going to be hard. But a much better algorithm is something that we already did while doing the PageRank algorithm. That is called power iteration. So start with any random vector, normalize it, and multiply A, the matrix whose eigenvector you're trying to find, and then replace S with that vector. So that's the idea. So it will converge to the dominant eigenvector. It will always converge to the dominant eigenvector. Now, once you have the eigenvector, then you can see that the eigenvalue can be easily computed by something called the Rayleigh coefficient, which is S transpose AS. So AS will just become lambda S, because S is an eigenvector. So lambda times S transpose S divided by S transpose S will give you lambda. So there are a couple of limitations for this. It is kind of sensitive to the initial guess. If you guess poorly, then you may not converge to the dominant eigenvalue. That is one thing. And for complex eigenvalues, you need to start with a complex initial vector. Otherwise, you may not actually get to the eigenvector. These insights are actually from either a website or a video, and I have the link to it in the textbook. Now, much better algorithm would be the QR algorithm. This uses the fact that similar matrices have the same eigenvalue. So our idea would be to get to a similar matrix starting from A, and hopefully that similar matrix will be something like a triangular matrix. And if it is a triangular matrix, then the eigenvalues are just sitting on the diagonal. It's a very imaginative algorithm, and it gives you an idea about how you translate these concepts to real solutions. So all we need to do is to find a similar matrix that is triangular. So we will start from the Gram-Schmidt process. We will take A and find its orthonormal version, and we will say that is equal to QR. So once we have Q, it's very easy to compute R, as you know, and we know that R is an upper triangular matrix. So R is just Q inverse A, but Q inverse is just Q transpose. The algorithm goes like this. What you would do is to run the Gram-Schmidt process, the QR decomposition, and set up the first A0 is equal to the QR decomposition. So first A0 will give you Q0. A0 is Q0 R0 because A is QR. But what about RQ? If you think about RQ, then you can multiply on the left by I, which is Q0 inverse Q0. And if you look at that, you can see that Q0 R0 comes here, and Q0 R0 is A0. And so R0 Q0 and A0 are therefore similar. They are similar matrices, so their eigenvalues are going to be same. So that is tricky and interesting how they thought about that. Now what you do is just set A1, next iterative step, to be R0 Q0, because we know that the eigenvalues of this guy will be the same as the eigenvalue of that, so we can deal with this and keep doing it. Finally, you will converge to something that is an upper triangular matrix. So the algorithm by itself is actually extremely simple to write. What you would do is take the matrix A and find its QR decomposition. So get Q and R, and then just place RQ in the place of A, and they just keep repeating it. QR algorithm has some numerical stability issues, I believe. So people have modified it, and there are better versions of it. Summarizing all the algorithms that we've seen so far in this course, if you want to solve equations, a really bad idea would be to go the route of determinants or Cramer's rule. A much better way would be to do any kind of row elimination, Gaussian elimination. If you want to find inverses, again, determinants would be really bad. Do Gauss-Jordan. If you want to do eigenvalue decomposition, bad idea would be to take the characteristic polynomial and then run some kind of iterative solution to find the roots, or do something more imaginative like the QR algorithm. All these algorithms actually correspond to some decompositions, so let's just list them for the sake of completeness. Gaussian elimination takes A to P LU. It applies to any matrix. P is a permutation, lower triangular matrix, upper triangular matrix. Gauss-Jordan will give you the inverse as long as the matrix is invertible, so it's a square invertible matrix. Gram-Schmidt will give you Q and R orthonormal and upper triangular. And eigenvalue decomposition will give you the eigenvectors in a matrix and eigenvalues in a different matrix. That would be diagonal. Now there is one decomposition that is quite significant. We haven't mentioned that at all. It's called Cholesky decomposition. So any positive definite matrix can be written as a L transpose, where L is a lower triangular matrix. And this has significant applications in simulations. If you have a multivariate normal distribution that you want to simulate, that you want to use in your simulation, that means you have the covariance matrix and you want to generate random numbers based on the covariance matrix. In other words, you generate a large number of random numbers and compute the covariance matrix. You want it to be the same as the original covariance matrix that you started from, which is not an easy problem to do. And Cholesky decomposition is the method that will let you do that. In the textbook, I have described this quite well, but that description actually came from a video that is linked to in the textbook. And the guy who was presenting the video is actually a computer scientist, not a mathematician. Well, I mean, he's a mathematician too, but he's more of a computer scientist. So his presentation is from the perspective of a computer science algorithm. So it's very interesting for you to watch that video, because it talks about not just how you propagate from one step to another, also about how you override certain parts of the matrix so that you save space, etc. Very nice video. And next week we will actually get to the king of all decompositions. That will be the singular value decomposition.